Hello everyone, my name is Santanu Samai. I pursued my BSc from Midnapur College Autonomous and currently I am going to join IIT Bangalore for integrated PhD program. In today's video, I am going to share my interview experience at HRI and this is my third interview. First of all, in the panel there were 4 professors in the panel. First professor asked me to introduce myself and they also asked me what is my interesting topic, what are my interesting topics. And then they start with quantum mechanics. And first professor asked me write down the wave functions, that is the superposition of two equally probable states. And simply I write the wave function psi equals to 1 by root 2 psi naught plus 1 by root 2 into psi 1, where psi naught and psi 1 to different state, and this is the probability amplitude. This is the 1 by root 2 and 1 by root 2 defines the probability amplitude for this state, and 1 by root 2 is the probability amplitude for this state. And then he also asked me to write down a normalized wave functions, that is the superpositions of two unequal probable states. So we write down the wave function a psi equals to a into psi naught plus b into psi 1. As the wave function is normalized, so root over of mod of a square plus mod of b square should be equals to 1. Then he also asked me draw the simple harmonic potential. We know that for simple harmonic potential, expressions for the simple harmonic potential is half m omega square and x square, and this is a parabolic graph. This is the v of x and this is the x and this is the origin, and this will be like that. Then he also asked me write down the expressions of energy, and we know that for simple harmonic oscillator the energy expressions n is n plus half into h cut omega, where n is the state, define the number of the state, order of the state of this simple harmonic oscillator. Then he asked me what is the expressions of initial wave function at later time t if psi naught and psi 1 defines ground state and fast excited state respectively for the simple harmonic oscillator. The wave function, the psi of t at time t should be equals to 1 by root 2 into psi naught into e to the power minus of I e naught t by h cut, where e naught is the ground state energy of the oscillator plus half into psi 1 into e to the power minus of I e1 t by h cut, where e1 is the energy of the fast excited state. And we know that for the harmonic oscillator E1 is the h cut omega by 2 and E1 is the 3 h cut omega by 2. So if we put this value here 1 by root 2 into psi naught into e to the power minus of I h cut omega t by 2, h cut cancel out and only 2 plus 1 by root 2 into psi 1 into e to the power minus of 3 I omega t by 2. Then he asked me is this wave function normalized or not? I said him that these wave functions also normalized. Then he asked me to prove this, and we know that to show a wave function normalized or not, we have to find out the bracket of psi 1 and bracket of psi, and it should be equals to 1 for a normalized state. And if we take the bracket notation instead of normal wave functions, then we can write psi of t equals to 1 by root 2 if we define the ground state like that. Now bracket of psi this is the expressions for bra of psi of t, and also we have the ket of psi of t, so it will be if we do some calculations, then we can find that half into plus half into we know that for simple harmonic oscillator the all the states are orthonormal in nature, means the bracket notation of the same state should be 1 and bracket notation of different state should be 0. Bracket notation of different state should be 0 where n not equals to m, and so half into, and it will be equal to 1 and plus half into 0 because there I have two different state, and plus it also 0 and it will be half, so basically we get 1. So psi of t should be normalized because we get the value 1. Then next professor asked me some questions on statistical mechanics. He asked me what is the Fermi-Dirac distribution function. And we know that Fermi-Dirac distribution function f of e equals to 1 by e to the power e minus ef by kt plus 1, where ef is the Fermi energy and E is the energy of the state, and K is the Boltzmann constant, and T is the absolute temperature. And then he asked me to draw this Fermi-Dirac distribution function for T equals to 0 Kelvin T equals to T1 Kelvin and T equals to T2 Kelvin, where T2 greater than T1 greater than 0 Kelvin. We know that for T equals to 0, Fermi-Dirac distribution function will be like that, and this is a step type function for T equals to 0 Kelvin, and this is the EF Fermi energy and this is 0 energy, and the value of EF here should be 1. And also for T equals to T1 and T equals to T2, it will be like that. This is for T equals to 0 Kelvin, this is for T equals to T1 Kelvin, and this is for T equals to T2 Kelvin. And then he asked me what is the Fermi level. From this curve we saw that at T equals to 0 Kelvin, below this Fermi level, the probability, the value of the f of e means Fermi-Dirac distribution function is 1, and the value of the Fermi-Dirac distribution function above the Fermi energy is 0. So we said that above which state the probability of occupancy of fermions is 0, and below which the probability of occupancy is 1 at T equals to 0 Kelvin, and this particular state is called the Fermi energy state. And if we take T equals to T greater than 0 Kelvin, then at which energy the probability of occupancy of the fermions is half, and this particular energy state is called the Fermi energy. And then he asked me some questions on electronics, and he asked me draw the Fermi level for intrinsic semiconductor, N-type semiconductor, P-type semiconductor, and also for diodes. For intrinsic semiconductor, we know that Fermi level lies at the middle of the conduction band and valence band, and this is the Fermi level. And for N-type semiconductor, for the N-type, semiconductor, the Fermi level shifted toward the conduction band. This is the Fermi level. And for P-type semiconductor, Fermi level shifted toward the valence band. And for diode, Fermi level should be like that. This is the p side and this is the n side, and the Fermi level should be at the same level on the both side, and this is the EF, and this is the p side and this is the n side, and this is the conduction band and this is the valence band, and also this is conduction band and this is the valence band, and this is the barrier potential VB. And then he asked me draw the band diagram for the forward and the reverse bias of the diode. For the forward bias, for the forward bias, we connect the positive terminals of the battery with the P side and the negative terminals of the battery with the N side. And we know that for the forward biasing, the barrier potential decreases, and the band diagram should be like that. This is the P side and this is the N side. This is the conduction band and this is the valence band, and also this is the conduction band and this is the valence band, and this is the Fermi level for the N side region and this is the Fermi level for the P side region. And this is for forward biasing, and due to this forward biasing, this barrier potential reduced by an amount V, where V is the potential of the battery, and this barrier, this difference should be equals to VB minus V for the forward biasing. And for reverse biasing, simply we connect these diodes with battery like that. Means the positive terminals of the battery connected with the N side of the diode and negative side of the terminal of the battery should be connected with the P side of the diode. And due to this connection, the barrier potential of this diode increases. Means this is the P and this is the N type. This is the P region and this is the N region, and this is the conduction band, this is the valence band, and this is the Fermi level, and this is also Fermi level for the N region. And the potential difference, barrier potential for the reverse biasing will be VB, barrier potential, plus the potential of this battery connected for the reverse biasing. Then next professor asked me some questions on mathematical physics. He shared a screen and he gave me some mathematical problem. And this problem was if integration of 0 to infinite sine of x by x into dx pi by 2, then find integration of 0 to infinite sin square x by x square into dx. Initially I got stuck at this problem, and then he gave some hints and I got these hints and solved this problem like that. We take x square and sin square x and we take this function u and take this function as a v, and then it will be like that: minus of 1 by x into sin square x 0 to infinite minus of 0 to infinite minus of 1 by x square into derivation of sin square x means 2 into sin x into cos x into dx, because we know that integration of u into v into dx equals to integration of u into dx of v minus integration of u into dx of ddx of v into dx. And after doing some calculation we get that if we put this infinite here, we get that minus of limit x tends to infinite sin square x by x plus limit x tends to 0 sin square x by x, and here it will be integration of 0 to infinite sin of 2x. We know that 2 into sin x cos x should be equals to sin of 2x, and x square it will be 1 by x, because integration of 1 by x square should be minus of 1 by x, not 1 by x square. So it will be 1 by x into dx. Here we saw that this will be 0 because sin square infinite is not infinite, but if we put infinite here, so we get that something valued by infinite means 0, and for this function we take that like that: sin of x by x into sin of x by x into sin x, and for this function we write this like that: 2 into x multiplied to here and also multiply to here, and for this here we know that limit extends to 0 into sin x by x should be equals to 1, and also limit extends to 0 into sin x 0, means here we get 1 into 0, 1 for this function and 0 for these functions, because if we put x equals to 0 here we get 0. So, and also if we replace 2x by y, then we find integration of 0 to infinite sin of y by y into dy. Basically these functions given here, and its value is pi by 2. So this is the final result of this problem. And then he also gave me another problem on mathematical physics. The problem was if z equals to x plus iy, where x and y belongs to real values, and then find the real part of cos of z by 2 into sin of z star by 2 in a short way. Initially I do like that. I put the value of z here, cos of x plus iy by 2 and sin of x minus iy by 2, and we expand these functions in cos of a plus b, in terms of cos of a plus b, cos of a into cos of b minus cos of a and cos of b. But he then said me no, in a short way. Then I think little bit and I do in another way. I multiply 2 and divided by 2, cos of 2 into z by 2 into sin of z star by 2, and half 2 cos a cos b, 2 cos a sin b, 2 cos a sin b. We know that 2 into cos a sin b equals to sin of a plus b minus sin of a minus b, and it will be sin of z plus z star by 2 and minus sin of z minus z star by 2, and it will be sin of we know that z plus z star. From here we can find that z plus z star should be 2 into x, and 2 into x by 2 should be equals to sin of x, and also z minus z star should be 2 into I into y. So this will be sin of I into y, and we also know that sin of iy equals to e to the power I into iy minus of e to the power minus of I into iy by 2 into I. So basically it is minus of I minus e to the power plus y by 2i, and we know that this is minus of 2 into sin of hyperbolic of y by 2 into I, 2 to cancel out, and if we take this I in the upper region, then we get I into sin of hyperbolic of y. So put these expressions here, we get sin of x minus of I into sin of hyperbolic of y So the real part of this function should be equals to only half into sine of x. Then he stopped. Then he told that this is enough for today and you can leave. And fortunately I got selected at HRI. Thank you.